Hello, students. We're going to be taking a set of notes on conservation of energy and energy efficiency. In order to do a good job on this, you need to have a loose slice of paper and set up your notes Cornell note style. We will be going kind of quickly, so if you need any time to catch up, please feel free to press the pause button at the bottom of this video and then carry on with the note taking when you are ready. All right, let's get started. So first thing you guys need to know is that there's law of conservation of energy is defined as a scientific fact. So it tells us that energy cannot be created nor destroyed. It can only be transformed from one form of energy to another. What this basically means for us is that once upon a time, about 15 billion years ago, when the universe was created, the amount of energy then is the same as the amount of energy we have now. So if you look in the diagram, this is a good way to think about the energy balance. So on the left side, before, I have a certain type of energy, E1, and I have some other type of energy, E2, but they stack to about this height. And on the other side, in the after side, I now have three forms of energy, but in total, they're the same height, so they balance out with the same as before. So what this tells me is that even though I have this new form of energy, E3, it was not created from any sort of a circumstance. Instead, it was probably part of a little bit of this E2 that got transformed into this new energy, or it's a little bit of E1 that got transformed into this. But either way, it was not created from scratch. This large E2 was not destroyed. Instead, it became converted into a different type of energy. So what this means for us is that mathematically, if we do algebra, this side of the equation and the before side should always equal or be in balance with the equation in the after side. That's essentially the law of conservation of energy. So we can use this concept of the law of conservation of energy to calculate energy efficiency. So energy efficiency is defined as the amount of useful energy you can get out of a system. So this lost or wasted energy is not destroyed, rather it's considered energy that becomes heat that's simply not useful to our purpose. And we'll talk in the next example as to what this actually means. So the next one is energy flow diagrams. So we're going to be drawing these diagrams along with your guys' help and a little bit of practice. So let's say we have a light bulb. In a light bulb, I have my initial form of energy, which I will begin right here. And in the light bulb, this form of energy that all starts with is electrical. Then this form of energy becomes two others. First, we get a little bit of solar radiant energy because the light bulb's job is to make light. That is its primary function. But also we get some of the energy that's wasted as heat. Again, it's not destroyed. It just does not go to the primary purpose of producing light. So this is our wasted energy as heat, and we all have felt this. If you try to unscrew a light bulb right after it's been on for a while, you will burn your hands. So this is going to be thermal energy. So again, we go from electrical, converting to solar, and converting to thermal energy. One of these is our energy flow diagram, and the arrows designate which direction this energy flow is taking place, and it also designate which conversions do we begin with and which conversions do we end with. But if we check for the conservation of energy, energy inputs, so things on the left side of the arrows, will equal to the sum of the outputs, things on the right side of the arrows. All right. Now finally, our energy efficiency formula. So these are all the formulas that we will need to use. So you guys are going to need to copy these down. Before you begin copying, please notice that we have this cursive E. That stands for efficiency. It is different from block letter E, energy output. So when you record these carefully, please note the differences in your notes so that you can use these. And I would put each formula in a box and press pause here and then go on when you're done. Finally, Let's get an idea as to some of these typical energy efficiencies that you might be experiencing. We have light bulbs that are regular, fluorescent light bulbs, car engines, batteries, electric heaters. And this shows you which energies they're transforming to and from. So for example, a car engine is taking chemical energy stored in gasoline and transforming it into motion energy eventually inside of the wheels of the car. Now, with this, I want you guys to fill in these 5 blue boxes and make your predictions as to what percentage it is. So for example, how efficient do you think is a light bulb? Do you think it's 99% efficient? Do you think it's 12% efficient or 15% efficient? Which amount of the energy actually makes it to become light? So fill this in, and I would recommend press pause before I show you the actual answers. All right, so my actual answers are something like this. The regular light bulb is around 2%, which is crazy to imagine that most of the light becomes heat instead of solar energy. My fluorescent light bulbs is a whole lot more efficient, around 30%. That's why everyone recommends that you replace your regular light bulbs with a fluorescent kind. A car engine depends on what kind of engine you have, but it's around 25 to 30%, so similar to what the light bulb does. A battery, such as a battery inside of a calculator, is 20 to 60%, and there's a large range of answers here because batteries can come in all sorts of types. And final electric heater, so if you use for example, a space heater, is around 75%. So what you probably thought is that your predictions that you made in this blue column were a lot more positive and optimistic than the actual predictions. So what we can learn from this is things are not as efficient as we imagine them to be. And there's a lot of energy that is wasted in ordinary objects that does not go to the purpose that we want it to go. For example, in a car engine, only 25 to 30% of the gasoline that you buy and you put in it actually goes into moving the car forward. The rest of it gets transformed into thermal energy and becomes wasted heat. All right, that's it, guys. Thank you very much for listening and have a good night.